Yeah, hello to everyone. It is a big pleasure again to be here today. And well, as Tony said, my name is Frances Wilhelmi. I am now working at Nokia Bell Labs in Germany. But before, uh, I was with CTTC, which is a technological research institution for telecommunications in Catalonia. It is based in Barcelona, a very nice area near the beach. And there is where I did this work, which is about the integration of blockchain in Open RAN systems. So, yeah, in today's talk, uh, it is basically about uh, one publication that we made, which is called Blockchain Enabled Network Sharing for RAN, and which was published in IEEE Network magazine. So you have the reference here in case you want to look at the paper, which is there is also an open access version of it, so you don't need to be members of IEEE to go to the paper. So today, what we're going to see is first of all an introduction to blockchain, because I don't know if you are aware of the technology that composes blockchain. And then I will explain the architectural framework where we integrate this blockchain technology with Open RAN. After that, I will show you some simulations, and then I will try to provide some highlights of the main open issues on the topic. So if that's okay, I will start with the introduction to blockchain, kind of high-level overview of technology. So yeah, basically, to introduce blockchain in a few words, we can say that it is basically a type of distributed ledger technology that is used by multiple entities to share, in essence, a database. The properties of this technology um, allow for a secure and reliable decentralization of the governance of that database, and this is the key point. So participants do not need to trust each other to participate, nor any trusted third parties needed. So to allow this level of security and trust in such a decentralized setting, information is typically stored in chronological blocks, as you can see here in the bottom, and one blockchain after the other. So this is why this is commonly known as blockchain, because it is a chain of blocks. And the chaining of these blocks is done using cryptography, which is the key for several properties that I will comment now, but which are basically related to immutability and security. So yeah, with this, basically what blockchain aims to do or to solve is to have a distributed database that is not owned by anyone. It is owned by all the participants and which cannot be tampered. So the information of the blockchain cannot be modified by anyone without the acceptance of the majority of the network. The way blockchain application works is more or less depicted in the figure, but I have more details later. But basically, we have a blockchain which is operated by blockchain nodes or miners. Typically, they can be the same object or entity. But the role of these miners is to take the transactions from the clients, generate blocks, and agree with the history of the blocks, which is basically what is displayed here. So let me show this. Yeah, before, if you're interested in blockchain and in blockchain for communications, we have recently initiated a series of tutorials for academic conferences. And here in this link, you have the full video of the tutorial that we gave to a blockchain conference in November. Okay, so yeah, to bring more context to the blockchain operation. So here is the basic scheme of the set of procedures that take place in a blockchain. So first of all, we have users or nodes which submit transactions, whatever their purpose is, to blockchain nodes. And these nodes, as said, they gather and propagate the transactions. And with those transactions, they generate candidate blocks. And these blocks, when mined, are spread throughout the entire blockchain network. Yeah, the mining concept is quite broad, but you can somehow see it as a computational effort that needs to be done to make the update of the blockchain system, the update of the database, legitimate for a single element in the network, the blockchain. So yeah, basically once blocks are forwarded, the other miners need to decide if they accept them or not. Basically, because they need to be legitimate to be there needs to be a consensus in the entire network to agree on the same history of the chain. So basically, this means that different miners can provide different extensions to the database, but only one can be valid at the same time, and all the blockchain miners need to agree on that history. So yeah, again, just to summarize a little bit the components that participate in a blockchain application. Here, I wanted to show you one possible way of representing the different blockchain layers. First, we have the application layer, which is the source of the information that needs to be stored in a blockchain. Several domains have blockchain applications: telecommunications, financial, supply chains, industry, insurance, whatever you can imagine. But of course, the most famous one probably is finance. And there is where you have cryptos like Bitcoin or Ethereum or others. Yeah, notice that the purpose of the blockchain is in a finance application is to simply exchange money among participants. I have some more details on this later, but for now, let's keep it like this. So the second layer is the consensus layer, which is about the set of protocols that blockchain nodes need to follow to secure the application data. So this is about agreeing on the history of the chain, so that all the nodes have the same database, which is fair. One example here of consensus type of protocol is proof of work, which is one of the most prominent examples and is typically adopted in public blockchains. But there are others like proof of stake or Rust or Byzantine fault tolerance set of methods and so on. Then we have the data layer, which is about the format and the structure of the data in a blockchain, which includes transactions, hashes of blocks, Merkle trees, and so on. And finally, there is the infrastructure supporting all these network layers, which tells us basically how a blockchain is actually operated. So if you operate it in the cloud, if you use virtual machines to run the intelligence of the consensus layer, and so on. So yeah, so far I know that all this may sound a little bit abstract, because I mean we are just providing a very quick overview of this, but maybe with this concrete example of electronic cash, you will see this more clearly. So yeah, as said, one of the main applications which was initially boosted by Nakamoto is through Bitcoin is electronic cash. No, Bitcoin was the first blockchain application in the world implementation, I mean, and since then it has kind of provided, a plethora of later applications in blockchain and evolution on that technology. But basically, this is about that you need to have several entities that exchange money in this case, but without the need of any third-party validator like a bank or Visa for credit card payments, so that you have a completely decentralized money exchange system. Yeah, okay. So in order to do this in a decentralized manner and without a validator, you mainly need two ingredients. One is security and the other one is trust. So you need entities to be able to trust each other that the money that they are sending to each other is legitimate and it can be spent. So basically, this can be achieved by making the information of transactions public. This is one of the things that allows to do this, so that anyone can validate what's going on, and also by providing immutable records. So if I make money transfer to someone, I cannot change it later and get back my money, basically. So yeah, to send money, basically the owner of it must sign a transaction using public-private key, and this allows to easily validate that the signature is legitimate, so that you can keep track of the money since till the origin of it. So yeah, again, since data has chronological order in the blockchain and anyone can know the status of the balance of each participant, this is very useful for trying to submit the transaction. And for anyone to be able to validate what's going on here. So yeah, again, the example, if someone has no credit, it can be known by anyone. So if that one is trying to make an expense or trying to send money to someone and he has not enough money in the balance, then all the network will know that and will prevent that transaction to occur. Basically, that transaction will be validated. Yeah. Okay. This is to finish with the blockchain part. Let me just show that there are many types of blockchains that can fulfill different purposes. And this is important for the use case that we are going to see today in the telecommunications domain. And I am saying this because the type of blockchains that we have just overbuilt are public and target some tough requirements that make them very slow and computationally expensive. So they are not very attractive from the industrial domain and from the point of view of telecommunication operators. But nevertheless, if you have an application where participants are more or less trusted to a certain extent, so you can use other types of solutions. There are other types of blockchains like private or consortium ones that provide much higher efficiency because of their design. Yeah, and the main difference between public, private, and consortium blockchains is in the reading and writing access or the level of governance of the blockchain. So basically, you can allow anyone to participate in a public blockchain, or you can allow just a set of stakeholders to participate in a private one, which could be the case of network operators. So what's the problem with network sharing and how blockchain can be useful there? So the main thing is that 5G and very soon 6G is increasing a lot the OPEX and the CAPEX cost for operators, mostly provided that they need to provide significant equipment upgrades to support like a new architecture as proposed by 5G. And also there are very new demanding use cases like ultra reliable low latency or massive connectivity that require to expend a lot of money on new sets of antennas and new technologies for addressing them. In particular, most of the costs for operators are concentrated in the radio access network, and this can be up to 70% of the total cost in a network. One example is again, is the shift towards the micro and picocells, which entails a lot of new deployments compared to previous big macro cell stations. So yeah, basically this is not sustainable, and this is where run sharing comes into play, which is the idea that multiple parties can share parts of a network and also split cost. Of course, run sharing is today much more feasible than before, especially thanks to virtualization and the openness provided by initiatives like Open RAN. But yeah, again, run sharing is good for sustaining the evolution of networks towards 5G or 6G, because it is good that we have new players coming in the market and that they share costs so that they can spend or make more investments in the network. This is clear. But the problem here is that having much more players in the game, like virtual operators, also entails much more overhead and chaos. About this, let me say that we can consider the implementation of SLAs, for instance, between operators or other players like service providers. And at the moment, SLAs are done manually and entail a lot of delays and overheads like back and forth emails and calls. To put an example, Deutsche Telekom here in Germany has agreements at the moment with more than 600 businesses. And each of these agreements requires a lot of paperwork and legal services to be done, and also monitoring and disputes. I mean, it's quite a mess. So, yeah, and of course, this is getting worse because this is the beginning of 5G, and we have a lot of new features and use cases in telecommunications that we didn't have before. And this is, of course, attracting a lot of new players, not only the telecommunications domain, but you can think about IoT, AI, analytics, whatever. So this entails that a lot of new people, new participants are going to enter into the game. So we will need for more agreements and more paperwork and so on. No? So here, again, the main problems of this are related to the automation, decentralization, and trust. And this is precisely where blockchain comes into play and starts as a promising tool for addressing scalability in beyond 5G networks. So as overviewed, blockchain provides properties like immutability, decentralization, transparency, security, etc. And these are expected to provide very important benefits to operators. Apart from that, blockchain would allow for the automation of many procedures like establishment and fulfillment of SLAs, as we saw before. And yeah, again, all of this is very useful for the use cases of run sharing that we're discussing today, and where ORAN would allow us to virtualize network assets and trade them as a service. So let's get into the architectural solution now. Just as a brief recap on Open RAN, which you must be very familiar with it. ORAN started by the ORAN Alliance, which is formed by operators and vendors in telecom to basically lower the cost of network deployments. And for that, they have written many specifications, including a novel, open, and intelligent radio access network architecture, which aims to foster interoperability among different parties. The ORAN architecture includes the SMO, System Management Orchestration, the ORAN Centralized Unit, OCU, which is in charge of higher L2 and L3 layers of the communication stack. Then the distributed unit for scheduling more real-time operations at lower layers, physical layers. And then the radio unit, where radio signals are actually sent and received. And in addition, it also includes the radio intelligent controller, which is actually split between the CU and the DU, and it provides AI applications like for traffic management or traffic prediction, traffic steering, or whatever. In this slide, you may find some related work on the application of blockchain to run, but I think I will just skip it by now to be faster. So let's get into the scenario. So this was our overall vision of the scenario where blockchain is used to exchange RAN resources in the context of RAN. So basically, the intelligent controller of operator 2. Here we have two operators, one in blue and one in orange. So the intelligent controller of this operator, operator 2, can detect that it will need resources from another operator, in this case operator 1, to take, I mean, to fulfill some of its services. Like I don't know, maybe it can be a handover, or simply it wants to allocate a slice for meeting some QoS or whatever. But the thing is that operator 2 is going to need some resources from operator 1, and this is noticed and triggered by the intelligent controller. So at the moment, this is decided. Then the operator can request for the resources through our blockchain system that is depicted here, so that they can automatically sign a contract that would allow for the provision of the service and the payment of the same. So yeah, based on the example of the two operators, here we have like a similar way of representing the architectural components. Here we have again the operator 2 in orange and the operator 1 in blue. And yeah, and basically we plot here the elements of RAN that take place in the communication, and also in highlighted in red, we draw the components, the new components participating in the blockchain system, right? So yeah, first of all, we have like a blockchain system, which could be, for instance, a permissioned Hyperledger Fabric blockchain, which is a type of blockchain implementation provided by the Linux Foundation. And this blockchain is connected, of course, with all the participants that can participate as well in the sharing of resources, of virtual resources. And yeah, and then we have like interfaces for the management of the same, or directly for interacting with the elements in order. So yeah, to interact with the blockchain system, here we kind of define it a RAN sharing broker with different components and functionalities inside. The first one is like a blockchain adapter, which would simply provide the interfaces to interact with the blockchain. For instance, the adapter could take some SLAs and convert them into a smart contract written in Solidity, for example. And apart from that, directly connected to admission control, there would be an auction engine. I will talk about this later, more detail. And this is to make or process offers for acquiring or leasing a specific service, but which comes through the blockchain. So let's move now to simulations. But yeah, before getting into simulations, let me explain what I was saying now about the action, because here we consider like two mechanisms for actually enabling the exchange of resources among operators. So first, we have a marketplace where infrastructure owners publish their services dynamically, and so that potential buyers can acquire them as needed. And the second one is an auction mechanism, whereby buyers publish a request for a service, and then potential sellers can submit bids to fulfill that service through virtual resources. And yeah, to be more precise, here we have the flow diagram of the auction case. So there is a first phase where the orchestrator decides to acquire a specific service, like a slice in operator one site. So based on that, this goes to emission control, and with that, a smart contract is done, like to request this service. Again, this passes to admission control for the other operator, which must decide if it accepts or rejects this service request. So based on that, it can place a bid based on, on the smart contract that is defined. So with the collection of bids, the smart contract can be closed and automatically enforced, so that the winner of the bid of the auction will be in charge of providing that service to the first operator in place. So after all this auctioning process happens, then we have the instantiation, for instance, of BNFs at the centralized unit or at the distributed unit, depending on the program services that are acquired. And of course, for the end of the service, we can also use blockchain for the charging and for enforcing the payment of the service that was fulfilled. And in addition, well, it is not put here, but the monitoring of the service could also be an input for allowing this enforcement of the smart contract, so that all the clauses in the contract could be like validated with monitoring data. This is the same for the marketplace, but maybe we can skip it. It is very similar. And yeah, and this was our simulation playground. So basically, we had a cellular deployment with random users spread and with resources distributed among 2, 4, and up to 8 operators and virtual operators. So here we evaluated the auction in the marketplace approaches enabled by a generic proof of work based blockchain implementation, and which were also compared to the static case where there is no dynamic agreement, so you need to have like long-term contracts if you want to share the network. Yeah, that's it. As for the metrics that we focus here, basically you consider capacity utilization, user satisfaction, and efficiency in terms of base station load with respect to the actual load. No? So for user satisfaction, we used this formula. I won't go into the details, but basically it includes a perception of the user towards the service that it gets in terms of the bandwidth allocated and the price it pays for it. Yeah, and for the blockchain, we also focused on the delay and the overheads that it generates to implement all this stuff. Yeah, if you're interested in the simulations, you can go to this GitHub, which is open, and the code is there. You can check that. Really. Okay. Yeah. Of course, here is the way that we characterize the blockchain delays, and here there is quite a lot of more work, because first of all we proposed a queue model in another paper, and we also provided like an optimization in another paper. But basically, this queue model is able to characterize the delay by a blockchain system, public blockchain system. And yeah, we validated this with a queue simulator. Basically, you also have the code of everything if you're curious. Okay, so yeah, let's now see some of the results obtained. So first of all, we focused on the performance improvements that could be achieved by the blockchain-enabled solutions. Um, yeah, based on the metrics that I showed you before. Yeah, I know the graph is a bit tricky to understand, but basically here we have like the different dimensions that I mentioned: capacity, satisfaction, and efficiency. And we have the same for the different number of operators that we consider in this cellular map. So yeah, we have 2, 4, and 8 operators, as you can see here. And the different colors are the different mechanisms. So the static one is the blue one, which is like at the bottom, which is basically that nothing is changed dynamically. So operators start with a certain amount of resources, and they use them to provide service to the users, their customers. And yeah, basically this is the output of the total capacity that they can have, the satisfaction, and also the efficiency. Then we have the auction, which is in red, and the marketplace in yellow. So they differ a bit in different aspects, as you see now. But yeah, basically, as shown here, both the auction and the marketplace improve the legacy situation in all the dimensions. But the auction is typically more efficient, as we could expect, and that the marketplace also provides higher capacity utilization. And basically, this is because offers are discrete in the marketplace, so that operators can obtain more resources than needed in the first hand, and this can be used later for allocating these already obtained resources to other new users that can come. So this in the action is the action is more efficient because you request what you need. But again, it entails more overheads because you need to place like one request per each service that you want to allocate and so on. Okay, this is about the overheads of the blockchain in terms of extra delay and in terms of overhead transactions per second. So yes, as before, we provide a comparison of the auction and the marketplaces for each number of operators and for different loads in terms of user request, which is characterized by this lambda parameter. And yes, we compare that. No, in this case, we didn't compare that with the legacy because the legacy has not any blockchain implementation, so the overhead here would be 0. Yeah, and the last, the delay, again, for validating a transaction in the blockchain. So it is like the time it takes for a user to request for some service to another operator until it gets the service through the blockchain. Yeah, in this case, as you can see, the delay increases a lot for the auction. As you can see here, especially when the load is high for lambda equal to 10. And typically the delay is okay for low loads, but yeah, you see that it scales up very quickly. That's becoming an issue, of course. But for the marketplace, in contrast, we find that it is a far more sustainable option because it allows for maintaining low delays even if the load is high and even if the number of operators is high, because here, as you may notice, the overheads in terms of transactions and also delays increase with the number of operators, because this means that there are more participants in the auctions or in the marketplace, but especially in the auction. So for every request, we may have like an exponentially increasing number of bids. No? Yeah. And for the overhead, the length is very similar, which makes sense. So yeah, to conclude this part, this is an interesting case with two operators, which typically helps to understand better what's going on. So in this first case, there is an operator owning all the resources. So the ownership is like 100% for one operator and 0 for the other operator. And yeah, and this depicts typically the case of a traditional operator which owns the network and a virtual operator which doesn't have anything on the network, right? And needs to acquire the network infrastructure from the first operators to provide service to the users. So here we made a kind of simulation and we plotted the temporal evolution of the users' received capacity and the user satisfaction. So in blue you have the capacity and in red you have the satisfaction. And we also plot like the mean base station load for all the sites in the map, right? Which increases like linearly in this simulation until reaching some threshold, which, well, until reaching the maximum in this case. You have the load and the satisfaction values here, which range between 0 and 1. And in the left, you have like the capacity values. So yes, again, as shown in the legacy case, many users do not get resources at some point when the load increases. And this also has an implication of a dramatic drop in the satisfaction. But and this is for the static case, of course, when no resources are dynamically shared. But if we focus on the dynamic case with blockchain, here you can see that it is more sustainable, no? That even if the load increases and the capacity decreases, of course, we can see that the user satisfaction is very high because typically all the users can be delivered a service thanks to the exchange of network resources by operators. And we did the same for the case where operators have like 50 and 50%, so they have equal split on the network. Again, we put the static here in the left, and yeah, we see that the same trend, that the capacity starts increasing with the load, but at some point it starts decreasing and getting stalled. But at the same time, the satisfaction is not as good as we could have because operators do not collaborate among each other. In contrast, for the dynamic case and blockchain case, we have like the same as before. So operators can exchange resources so that all the users are satisfied and all the demands are kind of fulfilled. Yeah, I think this is all. I have some conclusions here. So yeah, basically to conclude this, let me say that we saw in blockchain a very nice opportunity for automating network management by removing long-term interactions with third parties like regulators, like for SLAs, as we saw. Yeah, this automation, of course, can bring to use network resources much more efficiently, as we have just seen. And this can contribute as well to economic sustainability. Besides, given the openness that blockchain and ORAN can provide, we may have more competitive environments, so this would potentially lead to more investments and enhancement of the quality of telecommunication systems. So one example is that real global connectivity could be achieved with that. I mean, if we split the cost among many parties for building a network, and with this we are also able to exchange expertise and domain knowledge. So yeah, global connectivity could be a good target to be achieved. And also because of the properties of blockchain technology like transparency, mutability, so on, we can have like trust and reliability among network sharing players, as we just saw. So for the challenges, let me say that we saw that the communication overhead could be an issue, especially for the action system. Likewise, the transactions confirmation latency can also represent a critical aspect depending on the blockchain solution that you may adopt. For instance, if you adopt a public blockchain like Bitcoin, which takes like 10 minutes for validating a transaction, then you may not implement some real-time intelligence there, right? But again, of course, there are other blockchain solutions. There are many of them. There are infinite, I would say. And many of them are thought for the enterprise use cases and industry, so that the efficiency is in the range of milliseconds. So yeah, this can be used. Yeah, in our case, we use a super decentralized mechanism like Proof of Work, but again, this may occur to too much delay and overhead. And yeah, and for the stability of the blockchain in terms of consistency, it also has implications in terms of uh, of forking, which is a kind of splitting of the database, so that there are multiple versions of the same with some wrong data in some part of the blockchain. Yeah, and finally, I said that scalability is an issue and can become a huge problem with the kind of solutions that we considered in our analysis, which were public blockchains. But this is expected not to be an issue in other types of blockchains. Yeah, and that was all from my side. Here I forgot to update my new affiliation, but I mean, this mail is still operative in case you want to contact me. But if not, you can use the mail that I showed in the first slide. So thank you a lot for listening and for being here today.